the tools and all those stuff, I need to be a bit extra cautious because myself coming from the tool background, supplying the software tools, I got to be a bit extra cautious about what I'm going to talk. But having said that, I completely agree with all the discussions we had this morning. A tool is just a tool. How you use it, to what level of efficiency you use it, depends upon the understanding of the tool and the theoretical background which the user comes up with while using the tool and analyzing the results. So my discussion is going to focus on the current technologies for CAE, what ANSYS has been providing, and what ANSYS is looking in future with respect to solving most of the challenges that the industry is throwing at us. So when we are solving any analysis, like we say, like we are one of the biggest customers, biggest software providers of CAE solutions, and we aspire to be one of the leading software providers with respect to solving the whole of multiphysics. When we say that, we need to have capabilities to provide solutions for that. And what at ANSYS we have as a current technologies is that we have tools for design. You can build your own CAD model within ANSYS tools. We have tools for parameterization, tools for meshing, like a Gambit, which was used there, but then which is now being used as in the form of ANSYS Measure, ISM CFD, and T-Grid. And then using these are all some of the pre-processing tools, and then going further into the physics solution of the physics, we have CFD solvers, we have mechanical solvers, electromagnetic solvers, and coupled physics. So these are the tools which are actually providing the technical breadth that you will be able to cover various physics under one platform. You can perform multiple analysis. So at the same time, if you take within each physics, you can go to the depth and analyze in very detailed analysis of each of these physics. The morning discussion has been focusing much on multiphysics, providing analysis, not restricting ourselves to one physics, but extending it to physics beyond one discipline. And this is one of the best ways where you have the capabilities to model each individual physics, and then built upon the success and the strongness of each of these physics, you want to extend it to couple and do what we call as a multiphysics analysis. So just a brief background about what ANSYS as of now can do in different physics. Let's say if you're talking about aerospace industry, be it external aerodynamics, stow separation, aeroacoustics, landing gear analysis, fuel sloshing problems, impinging jets, gas simulations, and many more. I'm not listing all the applications, it's just to give you an idea of what ANSYS is capable of doing in aerospace industry. Then going to what ANSYS is capable of performing in automotive industry, we can do external aerodynamics, we can do noise modeling, aeroacoustic sound, aeroacoustic modeling, the underhood thermal management, component modeling, impact analysis, fatigue, and many more. Again, in turbomachinery, you can model the combustion aspects, you can model the loss prediction and the performance, the torque prediction, cavitation, crack propagation, and many more. These are all the analysis which we are doing individually at each physics. Now, while during my masters, like the professor who thought was fluid dynamics, he said like the idea of doing all this fluid dynamics is to capture two things: the forces and moments acting on the body, the resulting pressure losses, and the heat transfer effects. If you are able to do that, your fluid dynamics, the study which you are performing, the reason why you are performing the analysis is pretty much well done. But from the designer perspective of a product, what are these going to give as input? Fine, I know the pressure loss for this configuration. I know what is the force acting on this particular surface. What next? At the end of the day, I have to build a component. So these are the fluid forces acting on the body, and can the structure withstand these forces? Can a better angle or can a better geometry configuration minimize my pressure losses? So it boils down to performing a structural analysis, because at the end of the day, I'm going to build a structure. So how do I couple the information what I got from a fluid analysis to a structural analysis? Does it make a real difference, or is it just I can assume any approximate forces and design my structure? Extending to that concept, we are built upon what we call as a multiphysics. Your product will be much more accurate and much more reliable if I know the exact force distribution acting on the surface rather than approximating the force distribution and then designing my structural component based upon the actual forces that are acting on that component. So why do you need to consider it? Why do you need to consider multiphysics? You can't afford to ignore multiphysics, because the real world is much more complex than what we think it. The real world is much more complex than what we think it might be. The design depends upon coupled physics phenomena. Let's say you're solving for a motor problem. You would want to see the heat sources generated because of the magnetic forces, and those heat forces coupled along with the fluid flow might result in a different heat transfer phenomena which is going to affect your structural design, right? Is that important in your analysis? Maybe for relatively, if you're taking the factor of safety to a larger value, it might not be important. But in today's competitive world, each and every step that you take towards minimizing the weight, towards minimizing the cost is very much well taken and is the need of the hour. So you're faced with small errors or marginal stack-up effects, and then physical testing is too costly to take or consider the effect of all these phenomena. So in all these cases, it becomes pretty much relevant that you perform multiphysics. So innovative companies are moving beyond single physics analysis. So probably in, as we have discussed this morning, probably in 5 or 10 years down the line, there's not going to be any distinction between what is called as CFD analysis or what is called as an FA analysis. It might end up being called as an engineering analysis. So it might altogether come into a single framework. So in today's context, we have, say, a fluid dynamics problems where the idea is to get a solid temperature if you are solving for a thermal analysis, and the ideas, the quantities of interest would be the flow field, the pressure forces, or the convective heat transfer coefficient. And in the structural framework, we'll be talking about deformations, the stress strain, maximum deformations and stuff like that. In the context of thermal analysis, we talk about what is the temperature field within the solid, what is the resulting thermal stress, and in the EMAG field, we'll be talking about the electromagnetic fields and the currents, the resistive heating. But coupling these physics in an intermittent fashion is what we are calling as an FSA analysis, the fluid structure interaction, where we couple the fluid and the structural analysis, and we couple the thermal and the EMAG analysis for Joule heating. So what are the technologies what we have today to do these multiphysics analysis? There are two methodologies. Let's say one is you can do a load transfer, and the other is you can do a direct coupling. When we talk of load transfer, what I'm doing is that I'm going to solve individual physics first. I'm going to solve a CFD simulation, I'm going to solve a structural simulation, and then I'm going to say transfer the resulting forces in terms of, say, a fluid dynamic solution to a structural solution to get the deformations based upon the fluid forces. And then probably I may be transferring the resulting deformations back to my fluid analysis to see how the flow field is going to change with respect to the deformation that gets obtained. Whereas in the case of direct coupling, you do not do a load transfer. You are going to solve all these things in a single constraint equations. The equations what you are going to build up is not going to be decomposed of different physics. It's going to be composed of a single vector. So it's at an element level coupling and highly coupled physics. So you want to use a single model and the mesh where all the equations, all the relevant equations will be solved in one go. So ANSYS software utilizes both these simulation techniques. For the FSI analysis, the fluid structure interaction analysis, we're going to transfer the loads, and for coupled field analysis, we're going to use what is called as a direct coupling. So built upon this technology, ANSYS has always been looking into extending and increasing the user's ability to model real physics. And with that framework in mind, the first version of Workbench which came into picture, which was essentially making the user much more comfortable in increasing the usability levels to couple these data transfers. Probably, I mean, I recall about 4-5 years back, if I have to transfer one of the, say, fluid solutions to mechanical solutions, I had to follow a lot of methodologies, lot of steps in importing the proper surfaces, doing the mapping of the fluid forces onto the mechanical surfaces, taking back it to the structural solution and doing it the structural analysis. But with the framework of Workbench, you can do by click of a button. That's what we are talking about in terms of extending the usability of the tool. In a single project page, we can manage all the required analysis, be it structural analysis, be it fluid analysis, and then couple the data from fluid analysis to, say, a structural analysis. So you got a geometry, and then you got a conjugate heat transfer mesh, you got a CFD solution, and then you are passing on the CFD solution to structural analysis for thermal loads, then you're passing the pressure loads for the deformation analysis, and then you're calculating thermal stress solution. All these things in a single framework. You, as a user, you need not to copy any file from one location to other location. You need not to look into what exactly is going underneath. Again, with reference to the earlier discussions, users has to have an understanding what exactly is going on, even though you may not be aware of what specifically is going on, but you should be having an idea of what is expected out of it. So in earlier work, in earlier ways, you might be having a geometry built up somewhere, then you might be doing a fluid flow, you might be doing a structural analysis, might be doing a model analysis, and then a pre-stress model analysis. But with the framework of Workbench, you can do all these things in a single project schematic. What you got to do is that you got to just connect one solution to the setup of a different physics. So, and then specify the required surfaces where you would want to transfer the data. That's all you have to do. So, as an example, like we got this what is called as a piezoelectric capability. It's like the coupling of the structural and electric fields. So what you're seeing here is an example of a piezoelectric fan, where the element fields what you're solving for is structural and electric fields. And then thermoelectric coupling, you are actually calculating the EMAG forces and then coupling with the thermal analysis for a thermoelectric coupling. For example, of a thermoelectric cooler, and structural thermal electric coupling. So your structure is going to deform because of the thermal stresses induced, the thermal data which is being generated because of the electrical sources present in the domain. So far what we are doing is one step ahead of the competition with respect to solving multi-physics problem. Going forward and elevating the process, what we are coming up with R14 is what is called as a system coupling. At system coupling is it facilitates the simulations that require tightly integrated coupling of analysis systems, and what we mean is that you can couple any system to any system using system analysis. You might be having a transient structural analysis, fluid flow analysis, bring these two systems into the system coupling analysis. Tomorrow you might be having an EMAG analysis, fluid analysis, structural analysis, bring all these three analysis into system coupling and define the coupling parameters and set the data what exactly needs to be exchanged in the system coupling. So system coupling is going to be a generic interface where data from end-to-end and surfaces, end-to-end systems is going to be mapped and transferred. So as of now at R14, system coupling is capable of doing fluent and ANSYS mechanical coupling in one way and two-way two-way transient fluid structure interaction problems. Now, what we are saying is that fine, I got a problem and I'm solving multi-physics. I'm having my forces coming from fluid system and transferring it onto structural for doing structural analysis. Having said that, I am one step ahead of actually modeling and more accurately modeling my simulation. But then I really don't know what I'm going to change, what is going to happen if I change my mass flow rate. I really don't know what is going to happen if I change my inlet diameter. I don't know what is going to happen if I change my thickness. I would want to have an optimal solution which can give me the minimal weight of the component for the analysis that I'm looking at. So comes into picture optimization. There might be very explicitly specified tools for doing optimization. At ANSYS, what we are focusing is bringing different systems working together in a general framework and then do optimization analysis. So we are not restricting optimization to one specific type of analysis. We are looking at doing optimization in the framework of multi-physics, coupling different physics together and trying to get an optimization at for different aspects of different physics. I might want to have a specific mass flow inlet, specific mass flow rate, and I would want to have a minimum thickness of the structure for the minimal weight. We can do that. That's what we are actually aiming at. So for example, the scenarios like what happens if I increase or reduce the mass flow rate, how should the geometry change to maximize heat reduction, what can be done to mix out the species earlier, stuff like that. So what are the optimization methods what we have today? The fact that we have not one but more than one optimization methods to cater to various needs of the industry explains the fact that what ANSYS has been focusing on optimization as one of the mainstream application. We got what is called as an adjoint solver, predominantly in Fluent. We have what is called as a mesh morpher or shape optimizer. We have what is called as a design exploration and goal driven optimization tools. Coming to adjoint solver, it's a high level system view of conventional flow solver. You're going to solve the adjoint Navier-Stokes equations, the adjoint form of the Navier-Stokes equations, and then solve the adjoint equations to get the effect of different boundary conditions upon your solution. So the inputs would be the typical inputs for your what we do for a CFD analysis, like the boundary mesh, the interior mesh, material properties and stuff like that, and the outputs will be the contour plot in terms of the flow field physics, then the scalar values like the lift, drag and total pressure drop. Typically this is what we get out of a flow solver. What we get out of adjoint solver is I would want to minimize the drag. So what are the factors which are affecting the drag? By reducing which parameter can I minimize the drag? That is what is being addressed by adjoint solver. So you can take one engineering parameter which is the crux of your problem and see how that parameter is being influenced by various input parameters. Right. At mesh morphing, the body it's a geometric design change directly in the mesh in the solver. So you want to define specific parameters and then you perform a what if analysis to see what kind of results you're going to get out of various scenarios, then move the mesh internally within Fluent itself and then see what is the change it's going to bring out of it. So the process is that, like, what if case, it can be a mesh morpher, which means that you're going to set up the case and see the scenarios, what if conditions, like what if I'm going to change my inlet condition, what if I'm going to change my flow velocity and stuff like that. So you set up the case, you run the case, you set up the morphing parameters and define what are the regions which you would want to morph, and this is what is the shape optimizer. It will morph the required geometry, it will morph the required mesh to the parameters that you have set, gives the deformation and evaluate the results on the deformed mesh. And then you morph it again and it's a iterative process. You choose the best out of the design. Or you can do what is called as an optimizer. In optimizer you set up the case, you run the case, you set up the optimizer, define the regions and parameters and deformation of interest and then optimize. So it will try to iterate itself automatically, try to come up with an optimal solution. Right. And then Design Explorer. Design Explorer in that sense is a more generic tool that it uses, it kind of tries to embody the typical optimization tool. You want to set up what we call as a design of experiments. So for design and understanding the analysis response of parts and assemblies, you set up a specific parameters. It might be a geometric parameter, it might be a flow parameter, it might be the material property parameter. You want to define them as a parameters excuse me, and run it over a period of design of experiments to get a response surface. So out of all these design of experiments, you're going to get a response surface, and based upon the response surface, you create what is called as a goal-driven optimization. Out of these parameters, what you have specified, you may want to prioritize, saying that okay, fine, of the 10 parameters I have defined, I want to maximize parameter A, I want to minimize parameter B. For parameter C, it's of not much consequence to me. So likewise, you define your goal-driven optimization schematic and then try to come out with the best possible combination of the input parameters which is going to give you the optimized values of the given problem. You then actually perform the analysis with those parameters to fine-tune the design more precisely. So couple of examples on adjoint solver. Let's say you want to maximize the lift versus drag ratio of an airfoil. You actually define the parametric, define the areas where you would want to control the volume with respect to the adjoint solver, and then you run a sequence of analysis with different scale up ratios and stuff like that. So you end up getting too many design points, and if you look at the parametric value lift versus drag, you will be having one parameter which is giving you the maximum lift versus drag. So you adopt the geometry for that particular variation and perform the analysis again. So these are all the various combinations of the shape near the trailing edge, what you're getting for the maximum lift versus drag ratio. Another example using generic set and drag optimization. This was using the mesh morpher under the optimization tool. So it studies the various vehicle shape parameters and drag force. So what is the angle that the windshield is going to make? What is the angle that the back shield is going to make, and the side angles, so that it gives you a minimal drag. So you're going to define these as parameters run various analysis for those parameters. So it's the baseline design where you're getting certain flow field in the backside window. So this is the worst region where you're seeing a lot of backflow, and then this is the optimal design which minimizes the backflow and hence helps you in the drag behavior. Now fine, I got a optimized solution. I'm looking at a solution which gives me optimal solution, fine, but then I don't have a week to solve the problem. I got only 2 days to solve the problem. Can you help me with that? So HPC is the answer. As always, ANSYS has been spending and investing in R&D efforts of HPC for quite a long time, and it will continue to do so. So it enabling HPC adds tremendous value to your use of simulation while enabling the insight and enabling the productivity. So it's all about getting the better insight, not only getting better insight, getting it quicker, right? So the HPC enables high fidelity. So it enables design exploration and optimization at a much faster rate. The simulation, what it would take to perform probably in a week time, you may be able to complete in a couple of days time. So if you look at the trend and the investment that ANSYS has made over a period of years, it's continuous. It's not that ANSYS has stopped investing at HPC at one particular point of time and then picked up later seeing the trend. ANSYS has been investing in HPC continuously over a period of time. So with respect to the newly available hardware, with respect to the improvements in the hardware, ANSYS has been trying to keep itself up to date with respect to the hardware available, so that it can the solvers can get the best out of the available hardware. Some of the scaling improvements in ANSYS Fluent at R13. So if you see the graph, like in 2008, probably you might be getting a rating of 400, which rating typically indicates how fast a solution is getting converged. The higher the rating, the higher is the parallel scalability and the parallel efficiency. So way back in 2008, when we are using say 6.3, the scaling is not more than 400. But if you go to 2010, the rating has been improved for about 800, and also the number of cores where the scaling has been improved has increased tremendously. Going back to 14, the scalability has improved much.